Well, let's hope this would be the second of 3 videos, but I think we'll need to stretch our discussion of enols and enolates into a total of 4 videos. So in the first video, we looked at sort of the big picture of carbonyls reacting with something as a nucleophile. And the big picture, just as a review, was that we can have the nucleophile attack the carbon, and we had looked at acyl substitution and acyl addition, wherein that first arrow is drawn, and depending upon whether these are leaving groups or not, you would have acyl substitution with leaving groups, and if no leaving groups, then acyl addition. But in the first video discussing enols and enolates, it was mentioned that we can also have nucleophiles attacking the alpha protons to either generate enols or enolates. And before we get started into discussion of enolates, I just want to review what we did with enols. We discussed in the first video how we can, in any solution of ketones, any solutions of ketones or aldehydes, we can have some amount of an enol formed if it's an enolizable ketone or aldehyde, i.e. having an alpha proton. So for any ketone or aldehyde that has an alpha carbon, here I've circled that has one or at least one alpha proton, you can have an enol. So we discussed how that tautomerization can occur to give us some small amount of enol, small amount. And we also said that enols would be favored if you have no base in solution, and if we have an acid, they can be formed more quickly. It doesn't change the amount that's formed, but we can have equilibrium reached more quickly if there's some consumption of the enol in some reaction. Just really wanted to, before we get started into enolates, maybe give students an idea of how enols can tautomerize back to the ketone if we had no acid present. The catalytic amounts of acid in water, typically that helps us transfer protons if we have an aqueous medium, really gives us a different avenue for this tautomerization. We can protonate the oxygen and then deprotonate, like we showed up here in this sort of general, pattern we see for enolate chemistries. We have to tear a proton from the alpha carbon. So we could protonate first. If we were using an acid, we would protonate with an outside acid, this oxygen, and this proton would be that catalytic proton. And then water would tear off a proton from one of the alpha positions next to the carbonyl. But what if we had no acid and water present? How do we tautomerize from enol to keto or keto to enol? I wanted to just show you what could happen. We could take another one of these molecules if we had no acid, and we could propose sort of a thumb to pinky, pinky to thumb interaction wherein the pi electrons are going to reach out and grab this proton while the lone pairs drop back down. The pi electrons reach out and grab this proton, because we remember from enol chemistry this carbon here is partially negative, so this sort of makes sense. This could come back to a pi bond, so we could walk away where this proton's transferred back to the alpha position of this enol, and this proton from the enol over here is transferred back to the alpha carbon from this enol. So they pop away as two ketones. Now, of course, this would be a very slow reaction if we have to have that particular alignment of the two molecules. So that's why it's slow. But if we add a little bit of catalytic acid in water, of course, we don't need to have the protons come from the molecules. So we can have these protons kick things off in a different way. These that are coming from water can come to the carbonyl, and we can make the enol. So we can have this transformation back and forth because we're not, limiting the currency of protons to coming from the molecules. We've added protons that can come from water. So that's just something that wasn't mentioned in the first video that I really wanted to mention in this video before we start talking about the southern route here, base conditions. If you recognize in your solution a base, you don't want to do enol chemistry. If you have no base present and you're proposing something happening at the alpha position of a ketone or aldehyde, probably need to go to an enol. And we talked about how we could take an enol and attack, just like an electrophilic addition of Br2 started, pi bonds reaching out and attacking the bromine in Br2, but in this case it's enriched. It's more reactive than just an alkene, because the enol here, we have the OH feeding electron density more by resonance to this carbon. So that's where we attach this bromine that we'll say in time, this polarizability, we can attack one of those bromines and put it on this carbon. That was alpha halogenation of the enol, and that's what we discussed in the last video. Where I want to go now is discussing enolate chemistry. We're not limited to using enolates for these reactions, but it can be, I guess, it can be driven by an enolate, maybe in a more aggressive way. If we use a stronger nucleophile, we can drive these reactions to substitution products at the alpha position. We can drive these reactions thermodynamically. Could we have done any of these reactions with an enol? You bet. Can we have done it with an enamine? That's something that's not going to be discussed in this video, but near the very end I'd like to at least propose how they sit in between the enol and the enolate. Less reactive, more reactive, we have an enamine, and they're very often used in the body as nucleophiles. So in this video I'm going to try to just limit myself to just discussion of the attack of the enolate on Cl2Br2I2 enolates. The deuterated water I'm going to skip. We would have the ability to attack if we have base conditions, all where we're using deuterated forms of the base and the water. We could make a little bit of the enolate. The enolate could start attacking the D in water here, deuterium's the isotope of water where we have deuterium, and we could start deuterating the alpha positions of these carbons. We could take and replace all hydrogens if we use excess of this reagent, water deuterated and base that's deuterated. We could sub out all the protons at the alpha positions for any ketone or aldehyde that's enolizable. So I'm not going to discuss this one here. We're going to focus this video on just attack of Cl2Br2I2 with enolates and attack of alkyl halides. In the third and fourth videos, we'll be looking at, this will be the third video, we'll be looking at enolates reacting with class 2 carbonyls, that's ketones or aldehydes. In the third video, we'll also look at alpha beta unsaturated carbonyls. This is the alpha position, beta position. We can have beta unsaturated carbonyls. We can look at reaction of these compounds with enolates. And in the fourth video, we'll look at attack not of class 2 carbonyls, but of esters. What happens if we attack esters and carbonates? What happens if we attack these two types of species with enolate ions? And then finish up with some discussion of acetoacetic ester synthesis and malonic ester synthesis, with this, which is just a combination of reactions we'll have learned by that time. So a lot to cover in the 3 videos that remain. In this second one, I just want to focus on attack of Cl2, Br2I2, and alkyl halides. We'll be skipping in the discussion of attack of deuterated water. So what is an enolate ion? Well, we remember that an enol was just formed from a ketone by taking again the alpha proton, if we have one, and transferring it up to the oxygen in the carbonyl. This was the keto enol tautomerization, and we know that it can happen without acid slowly or with acid and water quickly. So the enolate is just enol minus the proton. So we make a more reactive form of the enol. It's more aggressive. It can be harder to control that reactivity because it's more basic than an enol, but it can drive reactions. This is more reactive. This is less reactive in general, just because it's less basic. We have, oops, I have my enol. If we had the enol, apologize, I thought that was my enol. We know enols are less reactive, enolates are more reactive. What we're showing here is resonance of the enolate ion, where we can have the negative, just made it a little bit larger, here's my lone pair, on the carbon. That carbon is negative, there's a huge lone pair, and we can drive the lone pair back down into a pi bond, kick the electrons up to the oxygen, and maybe this would be a more recognizable form of the enolate to the left, because it's really what we're forming if we take the proton away. But we need to know we have resonance delocalization of this negative charge to the alpha carbon. So that negative charge, even though it's more favored on the oxygen in the resonance form here on the left, we really find our products tend to form through the carbon that shares this negative charge by resonance. It has something to do with reforming the carbonyl, which is, even though it's a reactive bond, a carbon-oxygen polar double bond is very polar, they tend to reform, if they can, in solution. So we'll often draw the enolate ion through, as represented by this resonance form. We could have used this one just as easily, but you'll see in my notes that we often use this one because this is the carbon we attack things through. So here we have our phenylmethyl ketone. We have Br2, so we want to realize that this is a weak bond. We have excess of Br2. We have a strong base because this is positive and the oxygen has a full negative. So we're probably going to have to start things here. We do that, just kind of at least getting a first step in here. We have an alpha proton on this side, a benzene ring, the phenyl group being a benzene ring. We don't have at this carbon connected to the carbonyl. We have no protons, so there's no non-enolizable side to this. This is enolizable 3 times over, so we're just going to take one of those protons and we're going to leave the carbon that's next to the carbonyl, that alpha position. We're going to show that with the negative charge. Again, is this the only resonance form? No, it's stabilized by also delocalization into the oxygen, but we're going to draw it as such because this is where we tend to find reactivity is through this carbon, not through this oxygen. So that's the first step, would be to make the enolate. So we now know what's going to be attacking Br2. We would attack Br2 through this carbon. Now this is a runaway reaction, so we do not favor just going through this reaction once. We would sub out a hydrogen that we'd ripped off with a bromine, but then we would do it again and again and again until we have every alpha proton replaced with a bromine. We would have done the same thing over here on this side if we'd have had alpha protons on the left side. We did not, because this is phenyl group is the benzene ring, and there was no proton on this carbon connected to the carbonyl. If there would have been, again, protons that are alpha over here, we'd have subbed them out with bromine, because it's a runaway reaction. Now, limited control of this reaction is seen, and therefore, if you want to go to the full alpha halogenation, that's fine, but many times it's used just as an analytical tool in this way. If we make tribromomethylphenol ketone, tribromomethylphenol ketone, if we make that, this becomes not a great leaving group, but a good leaving group. This tribromo, trichloro, if we would have used Cl2, triiodo, if we would have used I2, we get a pretty good leaving group. And if we take then one more equivalent of sodium hydroxide, So 3 to get the bromines on, but a fourth equivalent to make an acyl substitution reaction go, wherein this strong base will kick off a weaker base, and we will have abstraction of that proton from the weak base to give us a halo form, a bromoform here as our guess leaving group plus a proton from that oxygen that attacked. So this would give us a weak base, our carboxylate, and this reaction would then be carboxylate, sorry. Okay, I spelled that wrong, carboxylate. We would have our carboxylate anion, which is a weak base, replacing the strong base. This reaction, this acyl substitution reaction, where the OH replaces the tribromomethyl anion, but then the proton gets ripped off in that last reaction that's irreversible to give us a very weak base from what we started with, a strong base. So this is an irreversible reaction, and we can use this to test for the presence of methyl groups off of carbonyls. So they can be used as an analytical tool to test for methyl groups, because you cannot have this loss of the carbon from the carbonyl unless we have a methyl group having 3 halogens off of it. This last reaction is just an acyl substitution reaction where we can kick off a methyl group that's been replaced with all its alpha protons with bromine, chlorine, or iodine as a leaving group. We can test for methyl groups off of carbonyls. Alright, that's it for the attack of chlorine, bromine, or iodine. We can use any one of those 3 here in the presence of excess base to drive all alpha protons off and replace them with halogens. And if, again, we have a methyl group, we can have an irreversible reaction to kick off the halonium ion that, when protonated, gives us that haloform that we see here. Chloroform, bromoform, iodoform. This would be called bromoform. Alright, let's go on and look at use of the enolate ions for an alkyl substitution reaction with alkyl halides. There are a couple ways we can make enolate ions. We can use a bulky, strong base like LDA. LDA stands for lithium diisopropyl amide. Lithium diisopropyl amide. So this is a bulky, strong base. Well, bulky, strong bases like tert-butoxide only go after exterior protons, and if given a choice, it'll go for the protons that are at the least substituted carbon. Now I've put an amine here that's alkylated so that we do not have any protons off of this nitrogen. If we did, we'd tear them off. So we've alkylated this nitrogen, no protons, so that we pick on this carbon that has just 1. So we would tear that off, and we would have, because of the basicity of LDA, we would have near 100% conversion to the enolate ion. Now I've drawn it again in the favored form where the oxygen is carrying the negative charge, but we know this carbon's hot by resonance. But regardless of how we show the enolate ion, whether it be like this or using the one we said is going to show how this reacts, regardless, the enolate ion is near 100% formed from the ketone aldehyde, amide. Here it's a little bit harder because this amide reduces the partial positive charge of this carbon, which reduces the acidity of this proton. So electron donating groups, OH, OR, now of course this would cause a problem, that's acidic, but OR, NR, at the alpha position reduces the acidity of alpha protons off of carbon. So if this can go, we can certainly have ketones and aldehydes, which we have just an R group over here. The partial positive here is greater. The acidity of these protons are greater. It's important to remember that the reactivity order of class 1 carbonyls and class 2 carbonyls doesn't change from what you've learned, acyl halides and hydrides, aldehydes, ketones, esters, carboxylic acids, amides. As this partial positive charge increases, the acidity of these protons increase. That's important to remember. As the partial positive charge here increases, the acidity of these protons increases. That kind of makes sense, because if this partially is greater in partial positive charge, it pulls more from this carbon, therefore making these more acidic. In general, we know from OChem 1 that if we look at the balanced acid-base reaction and the pK of the acid on the left is lower than the pK of the acid on the right, then the right side is favored. We always move from lower pKa to higher pKa. This is the weaker acid in this acid-base reaction, so we're not going to go back. This is the stronger acid, pKa of 30. It's not a strong acid, but it's stronger than a pKa of 40. So we favor the product side because we've moved from lower pKa, 30, to higher pKa, 40. So the enolate's favored in a great degree, near 100% enolate ion formation. And we would have had that if this had been a ketone or aldehyde. It had even been more strongly driven to the right. Once these enolates are formed, they can react just like we've seen strong bases react with alkyl halides. So everything's in effect. If it's a alkyl halide that's secondary or tertiary, we'd get E2. If it's a primary, we get SN2. So let's look at some of that chemistry and we'll be done. Discussion of enolates reacting with alkyl halides. So we can use LDA, we've seen that, and we can also use a different non-bulky base, sodium hydride. Now sodium hydride is the opposite in terms of what protons it'll go after compared to LDA. LDA will go after protons on the least substituted carbon in a ketone. So these two sides, if it was LDA, we would go to the carbon that has the most hydrogens. But in the case of sodium hydride, we go to the most substituted site to get our protons. So this has two alkyl groups. We would favor abstraction of the proton from the carbon that has the least alpha hydrogens. Of course we have to have one, and this does. But if this was a methyl group, we would favor abstraction of the proton on the right here. If it was a hydride, or sorry, LDA, then the methyl group having 3 protons off of it, more accessible, would be favored. So we have this thing that's called the sort of kinetically controlled enolate ion formation and thermodynamically controlled enolate ion formation. If you're going to the most substituted site, you're kind of following the thermodynamically favored path, and sodium hydride generally does. But if you're going to the side that's most accessible, it's sort of the kinetic side. It just happens fastest there. It's irreversible. You stay on that side, and you typically, if you're going to go to that side, you want to have your reactions done quickly, because you let it sit around too long, the enolates will equilibrate to the more substituted side, the side that has the most alkyl groups off of it. So we have this term, thermodynamically favored, that's sodium hydride, kinetically favored. You're usually going to the least substituted site, least hindered site, if you're using LDA. So if we had, putting in the box here, we had an isopropyl methyl ketone, and we used LDA, unlike what we see here, the proton being scavenged off by sodium hydride. LDA would go after the less substituted site, least hindered site. And again, this would be the kinetically favored product, not thermodynamically favored. This would be the kinetically. So everything in context here, we'd have to run fast and low temps if we want to use this enolate ion. Sodium hydride would go after generally the thermodynamically favored side, the carbon that has the most alkyl groups off of it. So let's stick with sodium hydride. We've made the thermodynamically favored enolate ion. This is a strong base because it took a strong base to make it, and then so we can tag this alkyl halide as a primary RX, strong base, primary RX. We know we favor SN2 reaction, so we would just consider that attack as an SN2, alkylating the alpha position. There's no stereochemistry here that we have to consider. So we would just have the ethyl group added to the alpha, or substituting the proton at the alpha position. That's pretty straightforward. Hopefully, again, remembering these are strong bases, if we'd had a secondary alkyl halide, we might see more E2 chemistry. So we really are limited to primary alkyl halides if we want alpha alkylation. Okay, just to close here, before we go to two practice problems, electron donating groups on the other side of the carbonyl, again, reduces the acidity of the alpha protons. So having an R group here really doesn't reduce the acidity here much because the partial positive charge here is greater. But if we have an alpha proton on this side and an electron donating group, this was just an alkyl group, if we have electron donating groups, the partial positive charge here decreases, the acidity of those alpha protons decrease. So which enolate ion forms most readily? That from the ketone. That from the ester would not form as readily because the carbon in the carbonyl is less partially positive. Therefore, the alpha proton at this position is less acidic. Okay, again, don't forget in the next two videos we're going to be doing a lot with the enolate ion. So in review, what we've done just today is we've halogenated the enolate ion with Cl2Br2I2, or we've gone through a SN2 reaction with methyl halides. We could do this, or with primary RX we can do this. We can have SN2. But if it's a secondary, I cut two carbon-carbon bonds, one here, one here. This is a secondary RX. We're going to favor E2. We're going to favor alkenes being formed, not a substitution product where we've alkylated this carbon. No, it's going to just tear a proton off of this R group or off this carbon to give us an alkene. Well, that's it. In the next two videos, we'll be looking at enolate ions attacking class 2 carbonyls, ketones, aldehydes, and attacking in the fourth video esters. Bye-bye.